A really fun lesson on integral domains and abstract algebra. So what do we mean by integral domains? Well, integral domains are not quite fields, but more than rings. So we'll say that they are between rings and fields. And as I said, they're not quite a field, but they're more than a ring. And by the way, if you put this A right next to the word field, it reads a field and it means distant. You're welcome. Okay, now for a formal definition of integral domains, let's do this. In particular, integral domains are, first and foremost, they are commutative rings. And of course, for a ring, when we say that it's a commutative ring, we mean that star or the multiplication operation is commutative. Otherwise, with respect to plus or addition, all rings must be commutative because, well, rings are first and foremost an abelian group under plus or addition. Yeah? Okay. Integral domains are first and foremost commutative rings with a multiplicative identity. So some element that acts like the number 1 does with respect to multiplication and different from the additive identity or 0. Yeah? Okay. So far, all that integral domains are is commutative rings with a multiplicative identity. And only one more requirement, which is that integral domains do not have 0 divisors. Wait, what? What does a 0 divisor mean? Or what does it mean to not have 0 divisors? Not having 0 divisors means that if a times b is not equal to 0, unless a is equal to 0 or b is equal to 0. Okay, my wording was pretty poor there. Let me do better. So not having 0 divisors means that a times b is not equal to 0 unless a is equal to 0 or b is equal to 0. And I still find this a little awkward. So let's put it differently. So put differently, a times b is equal to 0, automatically implying a is equal to 0 or b is equal to 0 means that you do not have 0 divisors because, well, we're saying that there's no way to multiply two things that are non-zero and get to 0. That's what it means to not have 0 divisors. So you'll see an example, but having 0 divisors means that you take elements that are non-zero and then you multiply them and get 0. You're like, what? That could happen? Yes. I'll demonstrate with an example. So examples of 0 divisors. So if you take the integers mod n, and these are just two different ways of denoting integers mod n, then unless n is prime, the integers mod n for n not prime are full of 0 divisors. So the integers mod n contain 0, all of them contain 0 divisors if n is not a prime, which is to say unless n is a prime. Okay. All right, let's get specific. So specifically, if n is equal to 8, clearly 8 is not a prime, then we have the integers mod 8, and there 2 and 4 are both 0 divisors because, well, 2 times 4 is equal to 8, but the number 8 mod 8 is like the number 0. So you see what we mean now? Okay, cool. 2 is clearly not 0 mod 8, and 4 is clearly not 0 mod 8, so we took two non-zero numbers and multiplied them and got 0. So that's what it means to have 0 divisors. Yeah? And integral domains do not have 0 divisors. So the integers mod n, where n is a prime, do form integral domains. Yeah? Okay, cool. So the integers mod p are an integral domain. Okay. All right, so then to conclude, let's summarize. So you read it. This is just like too silly for me, but it's very accurate. So you read it. And final note is like, well, let's make the distinction between a field and an integral domain, because we said that integral domains are more than rings, but not quite fields. So if we take the integers with the usual addition and multiplication, notice that the integers form an integral domain. For the multiplicative identity, we have the number 1, that's an integer, right? and it's different from the additive identity 0, which is also an integer, right? And yeah, and they're an integral domain because they have no zero divisors. And the integers, like you can multiply two integers and it will not equal 0 unless one of the integers is 0, right? Okay, but they're not fields, because remember, fields require multiplicative inverses, and so with respect to multiplication, what's the inverse of, for example, 5? Well, it would have to be 1 over 5, but 1 over 5 is not an integer. Yeah? Okay, cool. And this probably goes without saying, but clearly both rings and fields, or rather, sorry, both integral domains and fields are a type of ring. They're just special types of rings, integral domains and fields, yeah? And the order is first integral domains, and then with a little bit of an additional requirement, we get fields. Yeah, cool. I hope you enjoyed this, and keep watching. Take care.